Hi everyone, welcome to GemChem. Now today's video is on Cycloalkanes part 1 video, and here we are going to deal with cyclohexane. Now before starting, this is a new topic in the BSc first year syllabus, and here we are going to deal with the initial concepts of cyclohexane. Here we will see symmetry elements in the shear form of cyclohexane, Newmann projection of shear form, and enthalpy change. Now already many topics of BSc first year syllabus is already covered. You can watch it. I will give the link of the videos in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Now first is that if we know about cyclohexane, then we always consider a structure like this, that is a hexagonal structure. But this structure is highly strained and thus undergoes puckering. Now what do we mean by puckering? Few atoms goes above the plane and few atoms comes below the plane of the molecule, and this is known as puckering. Conformational analysis by X-ray studies and electron diffraction was done by D.H.R. Barton in 1950, and he confirmed the concept of puckering in case of cyclohexane. So if you see here, for this structure we can only consider that these hydrogens are above the plane and the black hydrogens are below the plane, but in actual cases the carbon is also above and below the plane. So let us see. Now actually this is our cyclohexane ring, and this looks like this, like a chair. We start numbering the carbons like this. This first one carbon, next 2, next 3, 4, 5 and 6. And this carbon number 1, 3 and 5 lies above the plane, whereas carbon number 2, 4 and 6 lies below the plane. And if we want to see it, these are those carbons lying above the plane, whereas this pink carbons lies below the plane. And if you see here, then this bond is always parallel to this bond, whereas the blue bond is always parallel to this blue bond, and this green bond must be always parallel to this bond. So these are the essential criteria while drawing a cyclohexane ring. Now we will deal with the different symmetry elements of cyclohexane ring. So symmetry elements of cyclohexane ring in chair form. If you can see here, same chair form is being taken, and this is the structure. If we want to find out the symmetry element, first we will try to find out the principal axis. And we have already dealt with different kinds of symmetry elements. If you have not watched the video, you can watch it. I will give the link in the description box as well as the I button present above this video. And first here, the principal axis is C3. That is, if we position a C3 axis and rotate this whole molecule by 120 degree, then this one atom of carbon comes in 3's position, 3 goes into 5's position, and 5 goes into 1's position. And there is actually interchange of the positions of carbon, but the molecule as a whole does not go any change according to the structure. Similarly, the down carbon 2 goes to 4 and 4 goes to 6 and 6 comes to 2's position. Next symmetry element which is present here is C2 axis passing through the opposite vertexes. So we have 3 C2 axes passing through the opposite vertex. Now if you see here, one carbon is above the plane, whereas this 4 carbon is below the plane. As you will rotate the whole molecule with the help of this axis, particular C2 axis, then what happens is that this 1 will go down and come into the position of 4, whereas this 4 will go to the position of 1. As a result, the molecule will remain same. If we consider this axis, then 5 will come in 2 and 2 will go in the position of 5. Similarly for this one, if we consider, then the last thing which we will see is that 3 will go to 6 position and 6 will come into 3's position while considering this axis. So 1, 2 and 3 C2 axes passing through the opposite vertex. Now we will see the next case where we consider the C2 axes passing through the opposite sides. Here also same case happens. 1 goes to the position of 2 and 2 goes to the position of 1, whereas 5 goes to the position of 4 and 4 goes to the position of 5. Just a mere rotation. And if we consider the other symmetry elements right now, then there is also sigma, that is a mirror plane which is passing through the opposite vertex. So this particular carbon 6 will be reflected in 2, whereas this 3 will be reflected in 5. And this is how we can obtain a sigma D plane. Similarly, another sigma D is from here, and there is also another sigma D passing through 3 and 6. So there are 3 sigma Ds. Also you have to understand that the axis which is C3 passing through the center of the cyclohexane ring also contains a S6, a center of symmetry, that is I is also present in this particular molecule. So ultimately what we get is that C3 is perpendicular to 3C2, and when we observe C3 to be perpendicular to the C2s, then the point group which we require to derive is always D. And since the principal axis is C3 with a subscript of 3, so it will be D3. And there is also a presence of 3 sigma D, which implies that the point group must be D3D, and this is very important. Next we go to the structural details of cyclohexane ring. First we need to consider that the distance between the planes of the two carbons, which is above and below the plane, it is 50 picometer or 0.05 nanometer, and the hydrogens given in blue color, which shows that the hydrogens are above the plane. This implies that these particular hydrogens are known as beta hydrogen. Above the plane is known as beta hydrogen, and those hydrogens given in orange are alpha hydrogens below the plane. This is very important. But another name is given to those hydrogens which are present above and below and in the straight bonding pattern, and these hydrogens given in circle is known as axial hydrogen, whereas those without a circle is known as equatorial hydrogen. So equatorial hydrogen. This is very important. Next we should know that the distance between the two hydrogen is about 251 picometer, whereas distance between a hydrogen present in equatorial plane in this case is 249 picometer, whether above or below the plane. Similarly, if an axial hydrogen is considered and equatorial hydrogen is also considered, but in same plane, then its distance is 249 picometer. Though the structure is drawn like this, but actually there is some deviation. That is, this particular hydrogen which is given in blue color is not actually present like this. It is somewhat present in a tilted manner, 7 degree. It is tilted by an angle of 7 degree. This is due to the torsional strain of hydrogen and in order to accommodate the bond angle. And thus we can say that this hydrogen is actually not parallel to each other. There is an angle of 7 degree. Other angles which we need to know is that the angle between these two is about 111 degree 5 minutes in angle. And this particular equatorial hydrogens are deviated by an angle of in downside, so it is 19 degree 28 minutes. Similarly, this particular hydrogen is deviated in above plane, so it is plus 19 degree 28 minutes, and this is important to know. Next we will come for the Newmann projection of this particular molecule. Now for this you have to look the molecule through this side, and when you try to look from the side of C1, then you can consider this to be a Fischer projection. And in the Fischer projection, when we draw, we see that the front carbon is taken like this, and we see hydrogen is present here. Similarly, hydrogen is present here. This carbon is attached to one other carbon, and if we go to the backside carbon, then we can see here a hydrogen, in downside a hydrogen, and from here a carbon appears, right? Similarly, if we consider for this is the carbon 2, whereas this is the carbon 5. If we consider for another side, which is present is 3 and 4. So from 2, which carbon is attached? 3 carbon. So 3 carbon has hydrogens above and in the left hand side. Similarly, the C5 is attached to the back carbon, which contains the C4 carbon. So in this way we can draw the structure. From the structure you can easily obtain the Newmann's projection. You have to look from this side. So if you consider only this Fischer projection, you have to convert this Fischer projection into a Newmann projection. After converting this, you have to just connect the carbon 5 and 2 with that. This is also another Fischer projection, and we need to consider these two Fischer projections together with these two carbons joined in between. So if you see here, this is our original structure, and when we look through 1 and 6 in the back side, whereas 3 and 4 in the back side, and 5 and 2 here, then our Newmann projection comes to be somewhat like this. And this is very important to know how to draw it, because this drawing of Newmann projection of shear form comes. Now you have to remember that shear form is free from van der Waals interaction. As a result, there is very less chance of being any Gauche butyl unit. Now if you see here, what do we mean by Gauche butyl unit? Gauche butyl unit refers to this particular unit where we have in each carbon 2 hydrogens and 1 CH3 unit. Similarly, in the back carbon we will have a hydrogen and CH3 and hydrogen unit. So if you want to see how many Gauche butyl unit is present in cyclohexane shear form, you have to consider the Newmann structure, right? So from here you can see for the front carbon C1, we are having one Gauche butyl interaction present here, right? And for this one. Similarly, if we consider for C2, there will be also one Gauche butyl interaction, and from the another side for C3 also one Gauche butyl interaction. For C4 also there must be another Gauche butyl interaction, and thus this continues for C5 as well as C6. From different angles we can get one Gauche butyl unit for each of the carbons, and as a result we can get the enthalpy change from it. You have to know few important facts about this, that is this energy of each Gauche butyl unit, energy of each Gauche butyl unit is near about 0.9 kilocalorie per mole, and if you want to get it in kilojoule per mole, then 3.3 kilojoule per mole. And for this particular chair form of cyclohexane ring, we have 6 units of Gauche butyl, right? So as a result, enthalpy change of the chair form will be enthalpy change of chair form is equal to 6 into 3.3, which is near about 19.8 kilojoule per mole. And this value is with respect to a hypothetical chair conformation in which CH3 group are anti to each other. So here ends the topic. Hope this was helpful. Thank you for watching. In the next video, we will deal with the boat form of cyclohexane ring. So do not forget to like, share, subscribe and comment.